Okay, in this lecture we're going to cover the next part of our section 4.3 material on separable equations. And in this part of our lecture we'll talk about initial value problems. So in the examples that we had considered previously in this section, we were finding what is called the general solution of a differential equation. So notice that in our earlier examples, all of the solutions that we found depended on some general constant or some arbitrary constant, which we were denoting by capital C. So when we refer to a general solution, we're meaning that it involves the general constant C. However, in most physical problems that we will consider a little bit later in this section, we will need to find a particular solution to a differential equation that satisfies some condition of the form y of x naught is equal to y naught. Now, this sort of condition is what is called an initial condition. And the problem of finding a solution of a differential equation which also satisfies the initial condition is what is called an initial value problem. So a little summary here, some terminology that we're introducing. We would say that a general solution of a differential equation is a solution which depends on a general constant C or an arbitrary constant. And if we are looking for a solution of a differential equation that satisfies some initial condition, which would be a condition of the form y of x naught is equal to y naught. So let's say we know the value of our function y at some particular x value. Then we can find what's called a particular solution of the differential equation that satisfies our initial condition. And that type of problem is called an initial value problem, solving a differential equation that is also given some initial condition. So as an example of this, let's look at the following. We're asked to solve the initial value problem. Y prime is 1 plus y squared minus 2x minus 2xy squared. And here we also have an initial condition that y of 0 is equal to 0. So that is when x equals 0, y must also be 0. Now, in order to solve this equation, or in order to find our general solution first, let me see if I can show that this equation is separable. So rewriting it in Leibniz notation, the derivative y prime could be considered as dy dx, where y is a function of x here. And this is equal to 1 plus y squared minus 2x minus 2xy squared. Now in these last two terms for my right-hand side, I see that I could factor out a negative 2x, and that would leave me with 1 plus y squared for those last two terms. So if I think about the first two terms on that right-hand side, 1 plus y squared, as being grouped together, then I see on this right-hand side, I could factor out a 1 plus y squared, and I would be left with 1 minus 2x. So dy dx can be written as the product of a function of x only and a function of y only. So this is a separable differential equation. And in order to separate this, or in order to solve this, I'm going to separate my variables, x and y, and let's see what we have. So on the left-hand side, I would have dy over 1 plus y squared, and that would be equal to 1 minus 2x dx. And to eliminate the differentials, dy and dx on both sides, I could integrate on both sides. And my antiderivative on the left-hand side would be arctangent of y. And the antiderivative on the right-hand side would be x minus x squared. And then if I group all of my constants of integration on one side of the equation, say the right-hand side, I would have plus c. Now, in general, I'd like to try to solve for y explicitly. So to solve for y here, as a function of x, I could take the tangent of both sides, and I would have tangent of x squared minus x plus c. All right. So what I have here is an explicit solution. I've solved for y in terms of x, and this is called the general solution. Of that differential equation. It depends on this general constant c. Now, since this was an initial value problem, we need to try to, from here, find the specific value of the constant c that would satisfy this initial condition. Y of 0 must be equal to 0. So applying that initial condition, if I substitute 0 in for x, I would have tangent of c has to equal 0. So c would have to be 0. Since tangent of 0 is 0. So once I have the specific value of c that satisfies my initial condition, I'm going to take that value for c and substitute it back into the form of my general solution. And we would have y as a function of x is equal to tangent of x minus x squared plus 0. So this would be my solution. Since I was able to solve for y explicitly, this would be an explicit solution. So let's look at another one. In this next example, we're asked to solve the initial value problem x times e to the negative t. Dx dt is equal to t with the initial condition that x of 0 is equal to 1. So let's see if we can show that this is separable. So here I could rewrite this equation by solving for dx dt, and I would have t times e to the t all over x. So if I multiply both sides of the equation by e to the positive t, and then divide through by x, I would have the following. Or of course, this can be written as 1 over x times t e to the t. So the product of a function of x and a function of t. So this is separable. And in order to solve, I would first separate my variables. So we would have on the left-hand side x dx, and on the right-hand side t e to the t dt. And in order to get rid of the differentials, I would need to integrate on both sides. So on the left-hand side, we would have a simple antiderivative, 1/2 x squared. And to evaluate the integral on this right-hand side, well, we see that we have t times e to the t. We've got the product of two functions which cannot be simplified, and that suggests that we would need to use integration by parts. So let's take a look at evaluating this integral on our right-hand side. So using integration by parts, if I choose u to be t, then dv would have to be the remaining part of my integrand, that is e to the t dt, in which case du would be 1 dt, and v would be e to the t power. So rewriting our equation, we would have 1/2 x squared is equal to u times v, which is t e to the t, minus the integral of v du, which would be e to the t dt. So evaluating this new integral, we have 1/2 x squared is equal to t e to the t minus e to the t. And at this stage, once I've evaluated all of my integrals, I can include the constant of integration c. Now from here, we'd like to try to solve explicitly for x. So let's take a look at how to do it. We could first multiply through by 2. So I would have x squared is 2t e to the t minus 2 e to the t plus c. Now why not 2c? Well, it doesn't matter. C is an arbitrary constant, so 2 times c is just a new arbitrary constant. Let's just call it c. And now to solve for x explicitly, well, I would have x as a function of t would be either the positive or negative square root of 2t e to the t minus 2 e to the t plus c. Now we might ask the question, okay, well, we have x could be the positive or negative square root of this function. So which one do we want for this problem? Do we want a positive square root or a negative square root? And to answer that question, we could look at the initial condition. So when t is equal to 0, I'm going to need the value of x to be a positive 1, which means that I do not want the negative square root here. I want the positive square root when I'm solving for x. So for my explicit solution, I would have x of t is the positive square root of 2t e to the t minus 2 e to the t plus c. And I need to find the constant c that satisfies my initial condition. X of 0 is equal to 1. So, a little scratch work to the side here. If I apply this initial condition by evaluating my solution at t equals 0, well, I would have the square root of 0 minus 2 plus c, and this has to equal 1. So to solve for c, well, we could square both sides. I would have negative 2 plus c is 1. So c would have to equal 3. And now once I have the value of my constant, c, that satisfies the initial condition, I'm going to substitute it back into my general solution, and I have x of t is equal to the square root of 2t e to the t minus 2 e to the t plus 3. So this would be my solution of that initial value problem. And because I was able to solve for x explicitly in terms of t, we would call this an explicit solution.